Okay, I didn't practice this. I should have come in at break time an hour ago, but I didn't, so we're just going to have to wing it. We had a presentation this morning about HR and retaining people. When at 16, I entered a foundry, was put through a degree course, and I left. I was one of the 20% who wasn't retained. I made these things, turbine blades, that fly around in jet engines. In the mid-80s, I saw these being simulated on computers, calculated. And I went out to Germany and joined a little company called Maxima on the right there, and then a number of years later came back and became the agent for them. I've been doing this for the last 23 years, casting simulation, I'm a founder engineer. But I was looking at, I hope this worked, yeah, I was looking for a thing on supply chains and value creation, destruction between companies and organisations. I stumbled across this image. Agile supply chains that deliver best-in-class service do so at half the cost of their peers. What on earth is that all about? Okay. So then I started thinking about it, and I got the ideas of 3 monkeys. So this is the tale of 3 monkeys. And here they are. On the left here, you can clearly see that this is the foundry monkey. The design monkey, then there's the foundry monkey. You can see I should have practiced this. On the right-hand side is the foundry monkey, and that's me. And you can always tell a foundry monkey is the one with the hairy arse. Okay? So that's the foundry monkey. So design monkey on the left, tooling monkey in the middle, I should say, and the foundry monkey on the right. Now the 3 foundry monkeys, the 3 monkeys had 3 dads in their industry, and they were the design monkey's dad. He was a designer in the day when the world was grey, no computers, no CAD systems, on drawing boards. And the tooling monkey's dad, well, he worked in a tool shop, and there he is, and he worked on these tools. And there's the foundry monkey's dad. Can you see him? You can always recognise a foundry monkey. It's very clear, because you know why. And they wear hats and a bit of sand here, this is a foundry. So the foundry monkey's dad, and the design monkey's dad, and the tooling monkey's dad, they made cars, and here it is. It's the coolest car in the world, driven by the coolest guy in the world, and it's in the Dolomites, so it's obviously James Bond back in the 60s. So that's how the world used to look, but it went colour. And now you can have a Aston Martin. This clicker's going a bit quicker than I thought it would. You could have this Aston Martin. James Bond's still a cool guy, and here he is. And, oh dear, the clicker's going 2 clicks for 1. And this is just a little bit of video, and I found this as well. So, they don't let old guys be James Bond, because you'd run the girl over and keep the car. So I'm not going to be James Bond anymore. This rolls over 1, 2, 3, 4, 5, 6, 7. Any James Bond fans in the audience? World record, I think 9 rolls. But as you can see, the roof's still in one bit. Now, the design monkey on the left is actually called Richard Kingsley, Senior Designer Underframe at Aston Martin Cars. Okay? And I asked him about this, and he told me about this film clip, and he also told me about this. Dry Another Day. Bond's Aston Martin crashes into a lake on its way to its movie set. And it's being driven by a guy called, if we get up here, where's the little pointer thing? It was driven to the film set by Fraser Dunn, 29, of Leamington Spa, suffered only minor injuries after the supercar careered off the road, piled through a railing into the Italian lake. Despite the Aston Martin's roof being completely smashed in, Mr. Dunn freed himself, swam to the shore, and was released from hospital last night. So he got out of it. And as you can see, the roof's crashed in, but he survived. So this is not crash testing as they do it, but as they want to be. And a guy called Ben Alpershilling near the scene said the car was travelling very fast on an extremely narrow road. It's a dangerous stretch, not surprisingly it was an accident. So ironically, the car was being taken to the film set for the next James Bond film. So anyway, the design monkey's driving it, my clicker thing's not working now at all. He was alright. So the monkeys now have got to design a new generation of Aston. The design monkey, the guy on the left, he's a clever guy. So he doesn't do crash tests anymore, he has virtual simulations. And this is from Aston Martin, from Richard Kingsley, a simulated side impact test. So you can see James's head wobbling around here, you can see the exhaust assembly. This is the cross beam going across here. And this carries the transfer load across the car if you get hit. And this is made of castings. Any foundry in the audience? Any foundry monkeys around? This has got to take that whole load. So you want that to work. And they did a good job, the design guys, because it worked. And so what I was tasked with doing, along with the tooling monkey in the middle, is, oh God, what's his name? HCM Engineering. Simon Hansen. It's not. It's Tony Winstanley, the guy in the middle, who's made tools for 50 years. And so they're going to make this. So they sit down and they get a timing plan from the evil project manager. And it says, here we'll have feasibility, here we'll have the tooling, here we'll cut it. And the foundry monkey gets his triac mods. At the end of this, you get 5 weeks to sort it out after you've cut the tool. In a program that lasts for about 6 months. So 6 months from the start design, you've got to have a crash-ready car. And in May, they told me that you've got to have this ready to have 40 cars in March. And they hadn't finished the design yet. Great. This is going to be fun. So what are we going to do? The foundry monkey, they asked me, could I do it? And yeah, no way, can't do it. So the only way we're going to get to do this is if we think about it. And the foundry monkey, he's been off to a thing called GIFA, and he's seen some presentations on integrated computer-aided engineering, where you try and crush the development time by doing a lot of simulation work up front, working together as a team on your agile supply chain. So that's what we're going to try and do. So this is what the design monkey had given me, and the tooling monkey wasn't really interested. But now the foundry monkey's thinking, I've got some clever stuff here. He's taken the plastic strain plots out of this crash test and looked at where the casting deforms and where the heavy loads are going through. Okay? So the foundry monkey's talking to the design monkey and involving the tooling monkey. So they know this now, and this is integrated computer-aided engineering, and he's got his Magmasoft simulation, and he's done some very simple things, and he's seeing a lot of isolated areas of liquid up here, and this is going to be a problem, because that's going to have shrinkage in it, and that's exactly the place where the high deformation rates are, up here, okay? So we've got a problem, and the worst bit of the casting, really, so they've got some ideas. Let's stick some feeders on it, let's build some feed paths through it. So working as a team on their agile supply chain, the monkeys went away, and they started playing around with putting bits into it, adding feed bars in here, which had to be machined out. So when we got the machining monkey involved as well. This is all going on about 6 months. And they ran some simulation work, and they see that this one without feeders, this one with the feeders on top, no feed path. There's no point putting this big lump in there, there's not no feed path. The foundry monkey knows that, he's not so stupid. And he tells the design monkey and the tooling monkey what he knows. And so they move on through the process, talking to each other all the time, and they use some things called process optimization tools, which can change designs and shapes. You see on the left here, the feed path here is being changed automatically by a bit of software and multiple simulation runs. And what the foundry monkey's trying to do, he's trying to develop a feed path up one side of the casting to try and make this area sound by putting in this feed bar. It adds weight to the casting. And he's keeping his mates on the supply chain involved. And he's looking at the weight of the casting. This is the total weight of the casting and the feed path to add. So they actually took some weight out of the casting, and the design monkey likes that, because the casting's getting lighter. But he's putting in this feed path, this bit that goes up the, I'll get the pointer to work up the side here, and trying to develop it. An interesting bit of the project was, I've got casting here, but this is the steering tunnel, and the steering column actually bolts onto here. And they were cutting threads into these parts, and they didn't want to put a nut on the back. And we spent a lot of time and effort trying to make these bits here sound, but couldn't get there. So we persuaded the design monkey in the end, he's going to put a bolt on the back. He wouldn't have enough thread pickup. We did all that to try and help it out. And so we ended up with our model. Is this one going to some movies? I didn't practice this. We ended up with this as our model, and we actually put a sprue in the back here. We looked at cooling in the die. We got up to 20 virtual castings as we're going through here. We look comparing them all, different ways of doing it to see which way they solidify, and seeing what's going on in the back there. The clicker thing's not working. And this was an automatic, autonomous optimization tool with a parametric CAD modeler. What a load of rubbish. The software here is varying the geometry here automatically to try and get a feed path up over here. I want you to note this bit. I'm trying to get a feed path up here to try and get this part of the casting sound. I'll come back to that later. I was trying to develop a feed path up here. I've given up going up here. I'm going to put a sprue in the back, so the third sprue in the back to feed this bit up through here, and varying little bits around, so I'm varying the geometry automatically. And of course, which one works? So the foundry monkey has to work his way through all these, and at the end of it, we came up with a tooling model. And then he prototyped foundries in the room. We made no physical prototypes. This went straight onto 40 crash test and sales and marketing cars. But we got a fully featured tooling model from the Tooling Monkey that we could put straight into our simulation tools and check out the designs. And Danny mentioned about robustness. So we want this to work repeatedly. So we did some robustness testing, clever little foundry monkey. So this is a low pressure die casting machine, pressure time window, in which we allow these 3 points to wobble around in this design space, which they do in reality. It's never consistent. And we allow the temperature to go up and down between 8, 10 and 760 and 25 degree steps. We end up with 18 different possibilities, all which we calculate, and we look to see which one here is the best and how it varies and which one is the variation. So we're seeing this shrinkage in here that's always there, and we're seeing some porosity down here that's always there. So we did a robustness check, and it looks fairly robust. So these are all tools and things that the Foundry Monkey can do and talk to his design people with. So the Tooling Monkey made this die, and it turns up in the foundry, and yeah, you turn up and get your toes burnt, and it is a foundry. So there's the tool, and it went onto the machine. And we had to make 40 of these right first time. But the clever little Foundry Monkey also knew that he could do a heat treatment simulation, a machining simulation. There's another part they made for the damper that goes on the back of it. I won't talk about it too much. So they did some distortion tests using stress simulation models to see if the casting would bend or distort while it's going through it. And at the end of the day, this casting is designed by this team of people. The design engineer, tooling engineer, foundry engineer, and a machining engineer, but the picture only had 3 monkeys in it, don't forget, so I couldn't include the machining guy. And they've created this tool, and what they've actually done is they've turned this timing plan on its side. They've did a lot of stuff with web meetings, discussing things, modifying CAD models, sending simulation results backwards and forwards, and tried to do this integrated computer-aided engineering, a lot of simulation work up front, just a very small amount of work on the foundry. So this is going from a concept, not even a finished CAD model, in about May, to a crash test ready car in March. They did actually crash some of them. As a problem comes along with all this, this person here is the evil project manager, also known as salesmen and buyers. And they try and stop these people working together. And when they don't communicate and interact, at these interfaces between the toolmaker and the designer and the foundry, information gets lost. Okay? And that's where value is created or destroyed. And all he's interested in really is what's the casting like. He doesn't want to know how it's made, he just wants his bit in a bag cheaply. Okay? So, yeah, the monkeys managed to make it well, and they managed to design it as one team. My clicker's not working again. And so, what we've done here, compared to the dads that made foundry castings in the day and worked in foundry, the walls that used to exist between the design engineer, between the tooling engineer, and between the foundry engineer, we tried to break those down, because in the day when everybody was grey and the world was pretty grey, this guy had months and months to work on his design, a few years. This guy had months and months to work on his tool. This guy had weeks and weeks and weeks, probably months, to make a casting, to send the tool back to this guy, to then tell this guy they couldn't make it, and to know that you didn't have a car. And so all this stuff has been crushed down, and times have been reduced. And this is all possible today. And when it was actually made, I didn't want to go back there. This was the first casting off the tool, which didn't actually work because the tool was a bit cold, so it didn't really fill up there. But it's pretty much right first time. We've managed to get those 40 castings in March for the crash test. While I was thinking about this, forget the monkeys for a minute, this is a bit serious. I thought we had 5 phases to developing functional castings. And if anybody wants it, I can let them have it. Phase 1, we did a basic assessment of castability. Could it be made? Did we think it could be made? Phase 2, we looked at its methods and layout. Phase 3, we did all this integrated computer-aided engineering to develop a method for manufacture. Then in 4, we checked it. We checked it with a robustness check. We checked that it didn't distort, had the right mechanical properties. And then in phase 5, we went and made it. Prototypeless manufacture. And I've done this for my users, really. What do you do in phase 1? Concept designs from a potential customer. Who do you get involved? Very early stage developments, designers and foundry engineers. What do you do? Or what have you got? CAD model, no drafting, no fillets. If you're a designer, I don't know if there's any in the room, if you're a designer, at very, very early stages, show your design to the foundry people, to the tooling people, ask them what they think, get some good feedback from them at the very early stage. And then our Microsoft methods we use. Knowledge exchange, this is something, knowledge exchange, talk to each other basically. Every foundry engineer should know where the highly stressed areas are in every casting he's making. Most of them don't. And most of them don't because they don't ask for it, or the design guys don't give it to them. So if you're designing castings and you've got a stress loading map, give it to the guy that's making it, tell him about it. If you're making castings or somebody asks you to make a casting, ask them for it. That's one of the things really came out of this that was good. What alloy choice, things like that, because you could change the alloys, manufacturing costs and options, even things like this. These design people would like to know some of these costs, yields. If you do your simulation work up front and you really talk to one another, you can talk about yields and costs and that sort of thing. So creating value by maximising your yield, by minimising material usage. Then at stage 2, mature designs, most component features, early stage, designer, foundry, possibly a tooling engineer, filleted models, what do you do? Stage 3 is where you really start to hit it with a really big hammer, and mature design on all components, and this is where you really want to start doing your stuff. Commercial stuff as well starts to come in, and if you're a designer or buyer of castings, the earlier you nominate the foundry and get involved, and the life gets a lot easier, and that's where the problems come. If you want to keep that competition between foundries, they're not going to work with you. That's one of those issues. Full die assemblies at the end of it, you start with filleted models, and you've committed to a process route. You're going to high or low pressure. How many are you going to make? What sort of cost goals, if you like? You know, if you want a Formula 1 engineer, you can pay a few £1,000s for a casting. If it's going to be in my car, it's got to be a few hundred because I can't afford any more. I haven't got an Aston Martin. I never get the chance to be James Bond either. And all these results, all these communications, we had daily web meetings. We didn't meet up very often. We had daily web meetings. We were talking to each other over the internet. And we completely bypassed the project management system, basically. We went around them completely, we didn't even involve them. And we're going to determine how the casting is made, the machining locations, dimension implications, inspection, and feedback all as you go. Then on the 4th thing, you do the robustness testing. Danny mentioned it. Everybody involved. Does it repeat? Does it give you the same thing again? So virtual property maps, treatment, robustness checks, and tell everybody what you find, what's going on. And we can even map and give these results back to the design on FEA models, and then they can put that back into their crash simulations, because very often they're assuming homogeneous properties. It's the same everywhere, there's no defects. We can tell them where the defects are and they can take that into account. Sign off on the final method of manufacture. I've got one on the floor here, I brought it along today, but it's being made now, this casting. The interesting thing on it, you know what I said about looking down in the bottom here? Yes, down at the bottom here, this is actually about 8 months old now. Down at the bottom here, there's some shrinkage. The evil quality engineer's turned up and he says, I don't like shrinkage in my castings, get rid of it. So the foundry have got to jump now because the customer's saying, quality engineer don't like that. And the guy who's doing this at Shield Aluminium in Kettering, and the foundry making it, and the foundry engineer, Daniel Christmas, is working on it. I've trained him up. He's being pressurised to make some modifications to the process. And I showed there's these defects down here at the beginning. We couldn't get rid of them, so we left them. But this is the highly stressed area. It's not in a highly stressed area. We know that. And the design engineer knew that. And so it's not perfection, but it's fit for purpose. And just because a quality engineer turns up now and says, make it perfect, I've got to do my job, make it perfect. Don't mess with it. Don't bugger it about. It works. So, Were there predicted defects that couldn't be fixed in the casting? If yes, don't mess about with the tool to please a quality engineer. And that's come up just in the last month or so, 18 months in. The first ones have gone off and you can buy a car and drive around it. I haven't got one, so I can't afford one. Anyway, bit of fun. So, that's some of the simulation work we did. We did about 50 versions and optimisation designs and robustness tests. And those 3 monkeys, of which I was one at the time, I'm the one on the right with the hairy arch. You always recognise a foundry monkey. That is this agile supply chain, and it's a design chain. And I think we did deliver these best-in-class products. Nobody else made it, so there's only one tool, so half the cost of their peers.
Okay.
Any questions? I'll be glad to answer.